Hi, my name is Linn. Welcome to our talk on No Labels Required, Zero-Shot Semantic Segmentation with Foundation Models. Robots in agriculture, such as this ground robot, have the potential to improve current agricultural practices, increasing yield, improving efficiency, and environmental sustainability through automation and precision farming. To perform field management tasks such as automatic weeding, the robot must first be able to distinguish between crop plants and weed plants in the field. We do this in a task called crop weed semantic segmentation, where we take in as input an RGB image, and as output, we would like to assign every single pixel in the RGB image as either a crop, a weed, or a background semantic. Here, we mark crops as green and weeds as purple. We can perform crop weed semantic segmentation using deep learning methods, where we feed as input the RGB image to the model, and the model outputs the crop weed semantic segmentation. This can be performed online on any agricultural robot. However, we must first prepare the model in an offline process called training. In order to train the network, we must first prepare a dataset consisting of the RGB input images as well as the labels, or the desired output of the model. We then train the model by optimizing the parameters of the model over a loss function such that the output is closer to the labels. However, in order to obtain these labels, a human labeler has to annotate every single pixel in the picture to the correct class, and this is a very expensive and time-consuming process. Therefore, we would like to be able to perform semantic segmentation without using these labels. So today we will propose a method that requires no extra labeling and no training. That is, we would like to perform a zero-shot semantic segmentation that typically leverages foundation models instead of labels. So what is a foundation model? A foundation model is a deep learning model that was designed to be generalizable and perform multiple tasks. Typically, this is achieved by using a very large deep learning model and training over a very large dataset. An example of a foundation model is ChatGPT that takes in as an input text and outputs text. It acts as a chatbot. Another foundation model is CLIP that maps text and images into the same high-dimensional feature space. There is also SAM, or Segment Anything model, that takes in as input an RGB image and a pixel prompt that locates the target object. SAM then outputs the segment of the targeted object. Now we would like to see how we can use CLIP and SAM to perform crop weed semantic segmentation. Which brings us to our approach. We take as input an RGB image and we would like to output the crop weed semantic segmentation. In order to do this, we first segment all of the plants in a given input image. And this can be done in the following way. From the given input image, we must first obtain the point prompts to prompt SAM. Let's take a closer look on how we actually obtain these point prompts. We first start with our input image. Here is a dummy example. And we then divide this input image up into a grid. In each grid, we assign a prompt. With the normal SAM, the point prompts are set to be at the center of the grid. But since we are interested in the plant segments and not the soil, we instead set the prompts to the greenest pixel in each grid using the excess green index. To get the final prompts, we set a threshold for each prompt and remove any prompt that sits on a non-green pixel. From SAM, we will then obtain all of the vegetation segments in the picture. From these segments, we then apply CLIP to get the corresponding CLIP features. Now we have all the plant segments in the picture. We then have to distinguish between the crop plant features and the weed plant features. And we can do this by comparing it to a bag of features that we collected on an offline process. In the offline process, we use RGB images as obtained in a different field trial or from online sources and use no labels. We run the same process as described earlier to obtain all the plant features in these images. Instead of using labels, we use a clever heuristic to distinguish between crops and weeds. In particular, we assume that crops are the most common plant species in the crop field and that crops are uniform in appearance. For example, in a sugar beet field, the most common plant are sugar beet plants and that one sugar beet plant looks similar to another sugar beet plant. Conversely, we assume that weeds are uncommon, or at least their numbers are spread across a wide variety of species. From this, we curate a bag of features to only retain the most common or the most popular features that are the crop features. So let us take a look at how we can select crop features from all other features. Pretend these icons represent CLIP features. First, we select some candidate features randomly. Then, for each of these candidate features, we compare it with the remaining features by calculating a similarity score, where for similar features, we'll get a higher score. And we do this for every feature that is remaining that's not a candidate feature. And we repeat it for the second candidate as well. Finally, we choose the candidate feature with the highest score as the crop feature and keep this crop feature in our bag of features. We can then compare this bag of features of crops with the features that we obtained earlier to then identify segments as either crops or weeds. Here, when we compare our output with the ground truth, we see that we are able to segment the crops and weeds correctly even though no labels were used. Here are some more qualitative results on our sugar beets dataset. We also show that our method is able to work on another sugar beet dataset as well as a maize dataset. Thank you for your time.